This is a companion video to my earlier video given here in YouTube dealing with optimized connections of gas wells, or alternatively linking up sprinkler heads, irrigation lines in large parks or golf courses. The problem, simplified, could be given here, where we have a connecting point here and all these sprinkler heads or gas wells or similar must be connected in an efficient manner, namely minimizing trenching length as well as keeping pipeline costs, material costs, to a minimum as well. The conventional way to hook up sprinklers in a golf course or large park or something is this way, where you see the blue lines are the connecting lines linking up each sprinkler heads. These are laterals. You could have a main line given here and laterals connecting here or something of that nature. This is a conventional way to do this. Here's one of the many outputs of my program giving a near optimized location of the trench lines given by the dotted blue lines here. This has a total trenched line length of 408 versus the previous conventional layout of 430. Notice that you do have some branches, bifurcations here, where splits or connections must be made using a Y fitting or T's or piggybacked Ys or something of that nature. If you're using polypipe, you could get a bend in your line here for a few feet to accommodate the bend in each Y, given a T fitting. I'll show you another example of an output of my program. Remember from the previous video that the randomness built into the program will give you a different layout each time the program is run using the same input data. This is another example of a layout. This actually has the same trenched length of blue dotted lines of 408 as the previous example did. Recall the conventional layout was 430. This could be a significant savings in trenching costs if you have a large project. I'll show you a third output of this. Here's another one. This actually has a trenched length of 406. So every time you run it, you can get a different layout. One of the big advantages of this program is it gives you multiple different layouts, multiple different locations of lines between the various outputs to allow you to accommodate greens, trees, roughs, other areas where you cannot or do not want to lay your trenched lines. Up until now, I've only talked about the first stage processing, which is the program I've presented so far in these two videos. I like to do a second stage processing, which I'll describe in a moment. We'll use this final example. Recall that conventional linkage of wells and points consists of generally just going in straight lines here and then laterals out to the sides. In doing this conventional linkage, in this particular example, we get a total distance of lines of 436. Running it through the program presented so far, this is just one of the many outputs I got, and I've selected this to use as an example. What I'll be doing is making one small change in, rather than connecting this well through this line and branch, I'll do away with this and connect from here straight to here and here straight to here as an example for reasons I'll discuss in a moment. The important thing to make here is that this program I've developed, and you see one example of its output, is not a final stage. It's intended to be used as a tool. It is not a final mathematical direct optimum to the problem, although many of these will be very close. Again, the point is, don't be afraid to make manual changes if you want on any of these things, nodes and points, to see how it would affect the final outcome. Here's a plot of that problem showing both first and second stage lines. The first stage lines came from the previous plot, and these lines in the smaller red lines are directly from that previous output of my program, with the exception of right here where I made a minor change manually as I described previously. So the first stage, total line distance in red here and overlain by the blue actually here, was a distance of 418. Recall that the conventional way of just going up with straight laterals had a distance of 436. So there's a small improvement there. But the solid blue lines is the result of the second stage processing, which does even better. That has a distance of 403. The point I want to make here is how the second stage processing is done, shown in blue. It uses a very simple and direct technique of taking each node in red here, here, and so on, and making a very small adjustment distance-wise in a very small random radius around each node. One node is chosen at random from among the many nodes, and then a very small adjustment in the location of that node is made, and then the complete graph or plot is recalculated for total line length. If there's an improvement, that new point for that node is saved, and another node is selected at random and moved a very small amount, and the total length recalculated, and so on. So this is a simple, direct technique. Doing this runs in just a few seconds or less for a few thousand runs. And again, this final output is shown in blue here. So there's some minor changes. The final length in blue, again, is 403. So there is an improvement over where we started at 436 with the conventional line layout. The reason I made changes here and here is just to show an example where you may not want to do this kind of thing for practical in-the-field reasons due to difficulties in laying out these lines, more connections here and here, versus going straight across. You can do it either way, This type of optimum will save a little distance, but maybe you'd want to do this. The point is, this is a tool. Don't be afraid to make some manual changes, make multiple runs, and see what your links are. So that's all for this week. We'll see you next time.